All right, welcome everyone. Today we're going to start working on some of our equations for the different figures, surfaces, well later on surfaces, right? But the different types of graphs and work that we're going to see within our 3 dimensions now in a vector format, okay? So today is just a real brief introduction start with our equations for lines, okay? So this is from section 12.5 in the text. Let me share my screen, make sure I get this right, and we'll get going. All right, here we go. So I started from a heading there. We're looking at 12.5, just the first part of it, looking at these equations for lines. Okay, we're going to see it like in terms of that vector, the parametric form, and some other format as well for presenting these lines in space. So, right, a lot of the work that we're going to see in this course in general is going to build from our previous algebra, calculus 20A, first semester calculus work, but finding a way to kind of expand on that, generalize these more multiple dimensions, okay, 3 dimensions in particular. So let's just real quick, right, recall back from algebra, right, to get the equation for a line, in 2 dimensions, right, R2, we needed a point that our line will pass through and the slope, right? And what we're going to start to refer to in our slope, right, the direction that that line is going to move, right? And that slope we had called m before, our rise over run, our change in y over our change in x, right? That ratio of how we're changing the y direction, how we're rising or falling, how we're moving to the right after we leave that point, right? And so in that graphene model, we would start off at some known point, x naught, y naught, right? X sub 0, y sub 0, or x sub 1, y sub 1, if you so choose. We'd use our slope, the rise, the run, and we start to get other points. And depending on how we took that slope, we can go backwards, go in reverse, right? Reverse those steps. And we can start to slowly but surely build what that graph for the line would look like. And we can, of course, have our equation. Find that y-intercept, so on. All those fun problems we had gone through previously. So now, in 3 dimensions, right, in R3, how can we define, how can we express a line? This path that we're going to follow in 3-dimensional space. And again, kind of interesting to draw here to visualize. Okay. But if we have some line traveling in space, how can we represent that line? Well, it still has these concepts. We'd probably want to know some point that we're passing through in space. But now the slope is not necessarily just a rise over run. right? How far out in the x direction, y direction, z direction are we moving? So more than a slope, probably giving away our discussion here, what we're going to need is a direction that we're moving. Okay? So now we're going to start to bring in this parameter, this extra variable that's saying, okay, most often we're going to call it t for time, thinking with physics and whatnot, as time progresses, how is this particle traveling along that path, right? Which direction is it moving? Okay, and we can go backwards, right? Thinking about vectors again. If I take the negative, then we're going to flip that arrow over, same path, opposite direction, the way the arrow is pointing. Okay, so hopefully with that idea, with this kind of identification, we see we still need the same type of information. We need a point that we're going to pass through and the direction that line moves in order to find any location on that line throughout space. Okay. All right. So with that concept then, as long as we have a point to start and the direction we're moving, right? So kind of in a vector format, what our textbook uses, we can identify the location in R3 in that 3 dimensions, right? As this R, where we have our X, Y, and Z, right? So in this vector R, this is this vector pointing from the origin, that's where its tail will be, to any point in space, or in this case, on our line. Okay? So let me take this diagram away for a minute. We'll redraw it. So starting off in general, we can make this vector R point to a particular location, a point in space. Okay, so this is that point, X, Y, and Z. The vector with the bend brackets, right, tells us how far out in the X direction to go, how far in the Y direction, how far up in the Z direction that vector should possess, right? And the magnitude of R is just going to see the distance from the origin to that point is giving us this location. We can wait there at those coordinates, right? And so then, getting back to our line discussion, okay? So if I'm going to start at this point, then travel with my direction vector V for this line, right? The direction of the line telling me how I can get from one point on my line to the next, how far in the X direction do I need to go, how far in the Y direction, the Z direction, so I can kind of plot my way along that line, that vector V, okay? And that vector V, A, B, and C, those components, okay? So that anywhere along that line, let's put this little kind of dashed line, I guess. We can identify where we may be. Okay. So later on, right, that vector r, I know, pardon me for all the points, right, is just going to point somewhere along that line. It just depends on how far away we are from that initial point, right? And again, that's going to come in when I start to stretch, right? So what we can do to find this location r, we can take this r sub 0. This is our initial, our known point location, right? That first point we know. And then we can add, right? I'm going to leave some space here for a second. That vector v, right? My direction. I'm going to start at my initial point. Then I'm going to add. So like we're adding vectors, right? That to get that resultant vector starting here. Then I'm adding my direction to move later on the line, but following that path. So we're adding my initial point plus some scalar multiple, right? We're going to either stretch that if we want to find a point way down the line. We need to multiply that vector by some bigger number, right? 3 times that vector, 5 times that vector to give a point way down here. We can go backwards if it's negative. We can take small increments, little changes, 0.1 of v, 0.5 of v, so on. So that's when we get our parameter t. Okay. Right, there's this parameter, this kind of scalar multiple, this constant we can bring in. Now this is what this function depends on, right? So in vector format, r of t, r sub 0 plus t times that direction vector v. Starting off here, depending on how far along the line I want to go, we're stretching out that direction vector v as far as we may need. Okay. So there's this kind of vector function form for a line. As long as we have an initial point, that direction which we're moving, we can bring in, this is our variable t, this parameter that's going to be able to pinpoint, to locate all these little increments, points along our line. Okay. And so then with that, we get these different forms. We have our vector form, like I just mentioned. Okay. And so if I start to expand on that, right, that this r of t, right, that's going to give us our generic, right, any location on the line. T is that parameter, right, that r sub 0, x naught, y naught, z naught. This is my initial, my known point, v, a, b, c, my direction vector, the direction that that line is moving. So in some respect, this a, b, and c, that's like our slope in the x, y, z, how it's slanted in the x, y, right? How we're growing, decreasing in the x, y, and z directions. And then lastly, that t, that's just our parameter, right? That's just giving us our way of progressing along that line. And so then in that vector form, we can start to expand. So in this case, that XYZ location is going to be equal to X naught, Y naught, Z naught plus T times A, B, C. All right, so there's my R sub 0, R naught, T times, I know my T and plus sign get a little bit jumbled there, direction vector V, A, B, C. So then doing that scalar multiplication, adding, plus T times A or AT, oh, sorry, not the bracket yet, Y naught plus T times B, Z naught plus T times C. And so if I start to equate individually, we get individually these components for X, Y, and Z. Okay, and these are our parametric equations for the line. Okay, depending on what value for T you use, it has to be the same through all three. We can plug that in and get our X, Y, and Z locations with that choice of T. Right, so we have our vector format, we have our parametric equations, okay, and here that value of T being used must be the same for all equations, right, for all those components. Okay, and so that finally leads us to this last format. So if we have these three parametric equations, okay, if we solve for T in each of these, right, subtracting that Y naught, subtracting Z naught, Z sub 0, X sub 0 we did first, dividing by A, dividing by B, dividing by C. Each of these values for T have to be the same. So then, since they're all equal to T, then these other sides of our equation must also all be equal. Those ratios must be the same. Slide this up. And this is what we call our symmetric equations for the line, for a line in 3D, for this line that we were talking about. So as long as we have a point and that direction that that line is moving in space, right, that vector V we call it, it can be a unit vector, it can be any size vector, any magnitude, as long as we know that direction that we're moving, that parameter T will scale it so that way we can get individual points working along that line. Okay? All right, like I mentioned, I just want to introduce that for today, for this lecture. There's some problems in the book we can work on, and we'll probably go through in the next lecture, as well as our introduction to the equation for a plane. Okay, but again, I started thinking about that, hopefully a good kind of representation of how we use those vectors to find our location in space, following now this particle's path along this line with respect to that parameter t. Okay? All right, crew, if you have any questions, let me know. Otherwise, see you in the next lecture.